welcome to the Deep Dive. Today we're jumping into a corner of engineering that, honestly, we don't think about enough. It's the problem of moving huge, heavy things.
They're not up.
Exactly, not lifting them. The real challenge, the real danger, is controlling their journey down.
It seems so backward, doesn't it? I mean, you look at a pyramid or a modern skyscraper, and all you can think about is the sheer power it takes to get things up there.
Right.
But the truth is, the physics of safely managing a multi-ton load against gravity is, well, it's a completely different and far more treacherous problem than just overcoming it.
And that is our mission for you, the learner. We are going deep on the mechanics of controlled movement. We've analyzed sources covering everything from, the inherent dangers of gravity,
All the way to a fascinating hypothesis about an ancient Egyptian basalt break, a 4,000-year-old idea.
and how those ancient principles show up directly in some of the most cutting-edge rigging equipment used today in high-angle rescue.
It's a really incredible through line. Our sources based
Right, so right now we have half-inch rope, the same 175-pound load, and we are using every single rung on the device at this point. At this setup is the King Kong of setups. You're not going to get any more than this. And don't forget, we have people, we can move 3,000-pound loads with this setup. So if you look, even a 175-pound load will feed through the device. So there's no need to have to try to take a wrap off. Overloading doesn't really happen.
Same system to lower it down safely.
And that right there is the mechanical nightmare. It's what our sources call uncontrolled descent.
Okay.
When you lift, you are applying more energy than the load weighs. You are overcoming gravity. It's a stable state. You're in charge.
You're winning.
You're winning. The
Yeah.
second you switch to lowering, you're not in charge anymore. Gravity is. And it's an accelerating force. The moment your pullers relax their tension, even a little,
The load just takes over.
it wants to run away. Instantly.
So there's no automatic brake built into a simple pulley system.
None at all. There is no hands-free hold. If the workers stop pulling, the load doesn't just stop, it plummets. It requires constant, active human tension.
And human strength is a terrible brake.
A terrible, unreliable brake, controlled paying out under a load that heavy is exhausting and, frankly, almost impossible to coordinate perfectly. It's just fundamentally dangerous.
And this is where that term shock loading becomes so important. It's not just about the static weight, is it?
No, and that's the distinction that can lead to catastrophe. The danger isn't the 10-ton block just sitting there, it's the dynamic force.
A sudden slip.
A sudden slip, a jerk on the rope, an abrupt attempt to stop it once it's already running. That moment can spike the force on your rope, on your anchors, to many, many times the actual weight.
So an anchor that was holding perfectly fine during a smooth lift.
Could instantly fail under a 20 or 30-ton shock spike. And if that anchor goes, the whole line can fail. And that disaster radiates outward, injuring a whole crowd of workers.
And what's happening to the people actually holding the rope?
Well, if the load starts to run, that rope is moving at high speed under immense pressure. It's like sandpaper made of fire. It just tears through skin.
So you'd instinctively let go.
You have to. And that's the moment it goes from a controlled slip to a catastrophic freefall.
On top of all that, the one thing they are trying to use for control friction is itself completely unpredictable.
This is one of the biggest takeaways from our sources. Friction in a rope system is, it's volatile. It's not consistent.
Where do modern engineers put the control?
They put it into the hardware. Modern solutions are all about taking control out of unreliable hands and putting it into mechanisms designed for either automatic safety or really, really predictable friction.
Okay, let's start with something like a heavy-duty winch. How do they stop the load from just sliding backward when you cut the power?
Usually with a ratchet and pawl system, you can probably picture it. The pawl is just a little arm that clicks into the teeth of a gear.
Like a one-way gate.
Exactly, a one-way gate for force. It lets the winch turn one way to lift, but the second you stop, that pawl drops into a tooth and locks the whole system. It's an automatic mechanical brake.
Simple, but effective. Now, in something more dynamic, like high-angle rescue, you hear about progress capture pulleys. What does that do?
It's essentially the same principle, but for a rope. It has a built-in cam, which is a toothed locking mechanism. The rope can only travel one way up. If the load tries to move back down, that cam immediately bites into the rope and locks it solid.
So that solves the no hands-free hold problem.
Instantly.
And then for the actual controlled lowering, you have devices called descenders.
Right. And a descender, or a self-braking belay device, is designed to transfer all that friction from a person's hands to a shaped piece of metal. It uses specific geometry, sharp bends and wraps inside the device, to create predictable, consistent braking.
If hardware takes the load, not the person.
The hardware does the work. Your hand is just controlling the speed of the rope feeding through it.
That's a perfect lead-in, because that core goal, transferring a load from a lifting system to a predictable braking system, might not be so modern after all.
And this is where we get into the basalt pulley hypothesis. It's just a stunning piece of experimental archaeology.
It started back in the 1930s at Giza.
That's right. An Egyptologist, Siem Hassan, found this very curious, highly polished basalt object of peculiar form.
Just one, at first, a total mystery.
A total mystery. Then, later, a second matching piece was found. Now you have a pair. Hassan and his team noticed they were mirrored with this semicircular shape, and they suspected they were part of some kind of block and tackle.
Which makes sense. The first thought is, it must be a pulley, right? Something to reduce friction.
Exactly. The researchers who first tested this hypothesis treated them as pulleys. They thought maybe you'd lubricate them with oil or a water slurry. But the testing was a spectacular failure.
Oh, so...
They were, and this is the quote, hopeless pulleys. The rope didn't glide through the groove at all. It would aggressively bite and grip the hard basalt. It created massive friction. It was terrible for lifting.
And that failure was the aha moment.
It was the entire point. The inefficiency for lifting was the intentional, desired control for lowering. It was a conceptual leap. They realized these objects weren't pulleys at all.
They were brakes.
High-friction capstan brakes. They were designed to turn all that dangerous gravitational energy into manageable heat and predictable resistance. The goal wasn't to eliminate friction. It was to harness it.
Let's get into the physics of that, the Capstan Equation. It sounds complex, but the principle is actually pretty elegant, isn't it?
It's one of my favorite concepts in mechanics. It basically says that the braking force you get increases exponentially with every wrap of a rope around a fixed drum or cylinder.
So it's not additive, it's multiplicative.
Exactly. One wrap around a pole might let you hold double the weight. But the second wrap doesn't just add that same amount of braking, it multiplies what you already have. 2 wraps might let you hold 10 times the weight.
And the experiments with the basalt replica found a sweet spot.
They did. The 1080-degree sweet spot. 3 full wraps of rope around the basalt drum. With 3 wraps, they found they could control a multi-ton load with what they described as a feather touch on the slack end of the rope.
So the real power is in the predictability. It's math, not muscle.
That's the core insight. The capstan effect gives you consistent, repeatable, stable braking force. It doesn't get tired. It doesn't change with the weather. The descent becomes a stable, calculable process, which is exactly what you need when you're moving monumental architecture.
And the choice of material, basalt, that wasn't an accident either.
Almost certainly not. Basalt is an incredibly hard volcanic rock. It's perfect for a brake. It can handle the intense heat and the abrasion from the rope without cracking or degrading. It suggests a pretty sophisticated understanding of material science.
So the full hypothesis is a dual system.
It has to be. You use a low-friction block and tackle where you want everything to be efficient for lifting.
And then you switch over to the high-friction basalt capstan, the dedicated brake, for the controlled lowering. They separated the 2 functions.
They conceptually separated the problem of
Okay.
moving the load.
Okay, so this is the same system.
Brilliant.
And the reconstructions you can show these housings around the
This part, this
skillet-shaped structure. Were those just
this
decorative?
basalt pulley part now.
Experiments showed they were absolutely functional.
I've shrunk the
Without
part down,
compartments to guide the
so
ropes,
it's in there.
slack
So this is
lines
the braking
built
part,
what the researchers
the
called
center
slack
part,
rope chaos.
and these are the sheaths
A total
with
mess that would jam the system.
the pulleys inside.
Housing to functional architecture.
So each one of these,
Rope line isolated
she's-
from the line.
it's got a pulley inside.
Sophisticated control.
So you haul the load up, and the center ropes go slack. So you just pull keep a bit of tension on the center ropes, hold your load up, right? And when you stop pulling on this rope, they go slack, these go slack, and the center ones take up the tension. And then you can let this down. It's very, very similar. It's easy, the friction part of it acts as a brake. So you've got your pulley this side and your friction brake in the middle. The heavier the load, the easier it is to operate. There we go, it's lowering the load. These ropes are slack. It's a dual system. So you can see these ropes go slack in the centre. You have to keep pulling on this, but there's no load on it as such. But as soon as you let go of this, the load's taken up on these centre ropes, and with the three full wraps around the top one and the bottom one, it gives you the optimum friction. So there you have it. This third experiment brings the two previous together. This time modern components are used, not to replace the ancient idea, but to make it immediately visible. Here the system combines conventional pulleys with the directional elements inside the sheaves, in the form of one-way bearings. During lifting, the system behaves exactly like the standard block and tackle. The sheaves rotate freely, providing mechanical advantage. But when the load is released, the behaviour changes instantly. The load does not run away, it does not shock the line, and it stops. This happens because the system has separated two functions. Lifting and handling is by rotating pulleys, and control is handled by friction. The one-way bearings ensure motion in the lowering direction is resisted automatically. At that moment, friction becomes dominant. As the rope wraps around a control surface, holding forces increase exponentially in accordance with the Capstan Equation. A small holding force is able to control a much larger load. What this modern system demonstrates quickly and clearly is the same dual behaviour that may have existed in the ancient system. One set of components to move the load and another to control it. The modern bearings do not introduce a new principle, they simply make the ancient concept easier to observe. Seen in this way, the ancient basalt objects no longer need to function as lifting pulleys. Their role may have been the same as controlling elements in this modern system. The Egyptians may have used dual arrangements, conventional rope and pulley systems to raise the load, and a friction-based stone element to regulate the descent. This precision, seen in ancient stone construction, strongly suggests controlled lowering, not forced, not guesswork, but controlled. These experiments show that the hardest part of moving heavy loads is not lifting them, it's stopping them, smoothly, predictably, and safely. Sometimes the most powerful engineering solution is not reducing friction, but understanding how to use it.